Hello, IB. We are looking at 18F, and we are integrating now functions that have an input or a domain that is linear. So now we're specifically looking for any kind of linear domain, all right? So in other words, whatever you put into the function, so I'll use the word input there, remind us what we're actually doing. Any input that is written in a linear form. So for example, our input into the function e to the x, so x is linear. It can be written as ax plus b, where a is your coefficient and b is just a constant. So when we take the derivative of e to the x, we get e to the x. If we have e to the 2x, so again, 2 is now your a value. Remember that when we took the derivative, we wound up using the chain rule. So we would use e to the 2x, and then we'd have to multiply by the derivative of the input, or the exponent in this case, which is 2. So we wind up with 2 e to the 2x as our derivative. Let's take a look and see what happened. You guys are welcome to pause here and try these with me as well. But e to the 1/4 x, again, we keep our function the same using the chain rule, and then we multiply by the derivative of the exponent. So we wind up with 1/4 e to the 1/4 x. And then for our last one here, again, 2x plus 1 is a linear input. So we keep e to the 2x plus 1 using the chain rule, and we multiply by the derivative of the exponent, which is 2. So in all of these examples, we are multiplying by the derivative of the exponent, which happens to be the a value when you think of your input as a linear function. So that a value is what we wind up multiplying by. So we've been discussing for a while now that when we take a derivative, that's the opposite of when we integrate. So when we find the antiderivative, which we use for integration, we are now going to be doing the opposite operation as well. So instead of multiplying by the derivative of the exponent, we will now wind up dividing by the derivative of your exponent. So here, if we wind up taking the integral of e to the 2x with respect to x, we will wind up keeping the original function, again using the chain rule, but now instead of multiplying by the derivative of the exponent, we're going to divide by the derivative of the exponent. And of course we can check, because if we now take the derivative, all right, of our antiderivative, so I'll use capital F there. So let's take the derivative of this. We're going to wind up getting e to the 2x, keep everything the same, so over 2, multiplied by the derivative of the exponent, and you'll see how those 2's cancel out, and you wind up getting back to your original function, which is what we started with, e to the 2x. So reversing the process of differentiating, again, if we take the integral of e to the 1/4 x, we will get e to the 1/4 x divided by 1/4, and when we divide by a fraction, we multiply by the reciprocal, so we'll end up with 4e to the 1/4 x. And then the same for our last function, with respect to x, we wind up with e to the 2x plus 1, and we divide by the derivative of the exponent, so we'll wind up multiplying by 1/2. Now remember, all of these are open integrals, so of course we would add on a possible constant, so we'd have this plus c in all of our final answers, just to account for any constant that might have gone to 0 when we took the derivative. So looking at our first rule of the day, e to the ax plus b, if we have any exponential function with a linear input, we wind up keeping, again, the exponential function, because this is reverse chain rule, and then instead of multiplying by the derivative of the exponent, we will divide by that a value, and then add on a possible c. So now all of our a's cannot be 0 because we can't divide by 0, right? So we're just taking a look at what's possible for our anti-differentiation. All right, so rule number 1 is with our exponential functions. For our second example, we're looking again, we have a linear input, but now we have a linear input. So we've got this ax plus b linear function that's now raised to some exponent. But our exponents in this case are not going to be -1, because we know if we had a -1 and we tried to anti-differentiate, if we add 1, we'll get 0, and then this process doesn't quite work. So that gives us a different type of function that we'll look at in a moment. So for all of these examples, our n value is not going to be -1, anything except -1. So think about what we would normally do with the chain rule. If we were taking the derivative of this function, we would basically, again, think of this as your u, think of it as u to the third power. So the derivative of u to the third would be 3u to the second, and that u is actually 2x plus 5. But then we would have to multiply by the derivative of the ax plus b form, so that would be 2, and you guys wind up with 6 times 2x plus 5 raised to the second power now because we dropped one. So if we think about how we would work this backwards, if I wanted to get back to where I started, let me take the integral of 6 times 2x plus 5, all raised to the second power with respect to x. This 6 is a coefficient, so I could actually just take that out. So I'm going to put that on the outside. And now I'm just going to think about the reverse process for the 2x plus 5 raised to the second power. So I dropped one power when I took the derivative, so I'm going to add one power, keep my 6. I'm going to add one power, so now I have 3. I'm going to keep the inside the same because that's what the chain rule tells me to do, right? And then instead of multiplying by the derivative of the inside, I'm going to divide. So I'll wind up dividing by this derivative of the inside, which is 2. Now, notice when we did the derivative, we took this 3 and we multiplied it. So that's where we have this extra 3 now, right? But there wasn't a 3 in my original problem. So right now, if I just simplified it as is, I would have 3 times 2x plus 5 to the third power, which is close. But where does this extra 3 come from, right? So remember, we multiplied this 3 to make the 6. So when I reverse the process, I also have to divide by the exponent. So that means I also need to divide by 3, or multiply by 1/3. So that means I would have an extra 1/3 here, which would cancel out the 3. So I just wind up with 2x plus 5 to the third power plus a possible c. All right. So if I wound up taking the integral of a new question, so we'll look at 2x plus 5 to the second, which is similar to this one, but I didn't have the 6 in front of it, I would wind up having 2x plus 5, adding 1 to my exponent, dividing by the exponent of 3, but then also dividing by your a value because it is a linear input. All right, so I'd wind up with 1/6 times 2x plus 5 to the third. All right, so we have to take into account a few of the steps that we did forwards when we differentiated, now to reverse when we integrate. Let's take a look at the second example here. You guys can try this one on your own and then try to see what you guys would get with this integral here. All right, so take a moment and pause the video. All right, guys, go ahead and check to see how you did. If we took the derivative, you would wind up with negative 35 because of the 7 times the minus 5, which is the derivative of the inside. So now when I work backwards, I'd be dividing by that negative 35 and adding 1 to the exponent. So our second rule for today is if you have a linear input raised to a power where the power is anything except negative 1, we can just add 1 to the exponent, divide by the exponent, and also divide by the derivative of the inside function. So using that chain rule in reverse. Rule number 2. Looking at our third example, we have a natural log function. So remember, our natural log input must be greater than 0, but notice that again, our natural log is written with a linear form of our input. So again, this next set of rules will apply. If I took the derivative of natural log, it's always the derivative of the inside function, which for us would be 2, over the original 2x plus 5. So now that we're working backwards, what we need to consider is this 2x plus 5, right, could have come from the inside portion here, the input of our function. So we know that we're going to wind up with, if we have 1 over, we could rewrite this as 2x plus 5 to the negative 1, which is the exact rule that we said didn't work with our rule number 2. Remember, your exponent cannot be -1. That's because when you have -1 as an exponent, it's actually a natural log function. All right, so we know now if you can write it as an input to the power of -1, so a function raised to the negative first power, we have a natural log. However, we would normally wind up multiplying by the derivative of the inside. So this has a 1 as our numerator, and if we multiplied by the derivative of the inside function, we'd have a 2 as the numerator. So in order to get rid of that derivative of the inside function, we are going to divide by the derivative, which is the 1/2. And therefore, if I took my derivative of this as it is, and I multiplied it by 1/2, I would wind up with 1. All right, similar idea for the second example. I know that it's a natural log function because I can write 1 minus 5x as the negative first power. That signifies in my head, I know I have a natural log function, but I need to divide by the derivative of the inside, which is -5. So we'll divide or multiply by 1 over -5, and then add on your possible c value. And we get to our third rule, which is when you guys have a linear function, so ax plus b, which is in the denominator, so it is raised to the negative first power, I know that is going to mean I have a natural log function. And my natural log of ax plus b, again, it must be positive, anything you guys put in your natural log function, which is why these straight lines are used for absolute value. And then we divide by whatever your derivative of the inside function is. Last but not least, let's take a look at our two trig functions. So when we took the derivative of a sine function, and again, the input is in the form of ax plus b, so a linear input, we take the derivative of the outside function, so cosine, keep the input the same, and then we multiply by the derivative of the inside, which is this a value of 2. So we wind up with 2 cosine of 2x plus 5. So now if we're working backwards, the antiderivative of cosine is sine. We keep the inside function the same, but now because we would normally multiply by the derivative of the inside when we took the derivative, we're now going to divide by the derivative of the inside to get our integral, and plus a possible c. When we took the derivative of cosine, we get negative sine, keep the inside the same, multiply by the derivative of the inside, which is -5. So this winds up being 5 sine of 1 minus 5x. However, we know that the derivative of sine is cosine. So the antiderivative of sine is going to be negative cosine. So think about that negative value that needs to pop up in this last rule for today. So if I want to get sine, I need to work with negative cosine as my integral, 1 minus 5x, and I'm going to divide by the derivative of the inside, and then add on my possible c value. So I now have 1/5 cosine 1 minus 5x plus c. So if I checked my work and I took the derivative of cosine, I would get negative sine, but then multiplied by the -5, it would come back to positive sine. So I can always check by taking the derivative. Rule number 4, again, same idea for an integral of cosine. It's going to be sine, keep the inside the same, divide by the derivative of the inside function, and then for sine, your integral is negative cosine, and also divide by the derivative of the inside function. So just a reminder, if you guys have an integral of sums, then you can just take the sum of each piece or each term, and you can add all the integrals together. But if you have an integral of products, you can't just take the product of the integrals. You can't just multiply all the integrals together, which is why these 4 rules are in place, so that we can remember how did we take the derivative to begin with, and then how would I work backwards to find the integral. All right, so 4 rules for today. Go back over all 4 of them, and then we'll start with some practice when we see you guys next time.